and then I'll post this on YouTube later on.
Oh yeah, getting recommended your videos again.
You're getting recommended my videos because it's time to study, right?
No, it's just like.
I believe while I'm waiting, somebody had asked a question about back-to-back exams. I do want to bring up that chemistry and history are not back-to-back exams, to be clear. Chemistry is a morning exam. History is an afternoon exam. The morning exam, there is a key time of 9 a.m. The afternoon exam, there is a key time of 1 p.m. There will not be full center supervision in between the two exams. You will leave the chemistry exam, you will be able to eat lunch. You'll be able to eat lunch, and then you will go for your history exam. So that is the answer to that actual question. There is no full set. There's only full center supervision if you have back-to-back. Let's say you had 2 p.m. exams back-to-back or 2 a.m. exams back-to-back. You may have full center supervision in between. Or in one of those case scenarios like last year, where the 10th graders had to wait to take the chemistry till like 11 a.m. if you'll recall, you had full center supervision from 8 to 11 because of the fact that people were already taking the chemistry exam. You couldn't access any technology because people in the world were already taking the chemistry exam. So technically, Cambridge was very, very careful with making sure that the information for anything about the exam doesn't get out to the population. So that's why full center supervision exists and why you're not allowed to use your technology, but you are allowed to use your notes. If you'll recall, for that chemistry lab exam, you were allowed to bring your notes on the lab to study together while you were waiting for it. So just to be clear about that. All right, so let's go ahead and get started. I think this one should be shorter. It depends on how many beakers with anodes and cathodes you want to write. I was planning on only writing one, but if you want to write several, feel free. This is Unit 3. The topic is electrochemistry. Don't forget to have me pass out all the standards. I did print them out for you at the conclusion of this. Just a lot of handouts each day. For every unit, I wanted you to write down the formulas, any key chemical reactions you need to know, any definitions, and any common explanations. So that's really going to get you pretty far as long as you study it all for your paper 4. So we're going to start with formulas. One. And I wrote them in syllabus order, not in teaching order, the order that I taught them. So the first one is the Flea formula. Yep. The Faraday is defined as Avogadro's constant times the charge of an electron. That's what this formula is. It's the Flea. I'm writing them in syllabus order once again. The second formula in syllabus order is the quit formula.
Jesus.
In syllabus order.
The syllabus is fine already.
The first one's Flea, the second one's quit. This is the one that I'm going to put in parentheses underneath. I write it as C equals A times S because I like to have the units. It's coulombs is amperes times seconds. But Q actually stands for charge. I is current in physics, actually, and T is time. And the universal unit of time is seconds. And that's why it ends up being these specific units.
What's the first principle for being this?
Q is charge.
No, I mean for Formula 1. F equals
Faraday is the Avogadro's constant times the charge of an electron.
Remember Faraday.
You can find this all in your syllabus. The next one is standard cell potential. Standard cell potential. E cell is, I think the easiest way to remember it is the standard reduction value minus the standard oxidation value. So you have to compare your two potentials and you have to see what is reduced and what is oxidized. What is reduced, you're going to leave the sign, and whatever's oxidized, you're going to change the sign. How do we tell what's reduced and oxidized again? We just see it in the bow work, but what's reduced? The more positive E value is reduced, and the less positive or more negative E value is oxidized. So when given two E values, you have to compare the size, we call it the magnitude, and the sign of the charge. The more positive one's always getting reduced. The less positive one, or the one that's negative, is the one that's getting oxidized, and that's the one you would have to flip the sign for to do the subtraction. So that's standard cell potential, very, very common to be asked for this. And it's not worth a lot of marks, like 1. The non-standard cell potential, which is called the Nernst equation, is for a half cell at non-standard concentrations. What's non-standard? It's not 1 molarity. It's anything but 1 molarity. So non-standard concentration, anything but 1 molarity. You have to use the Nernst equation for it, which is the E cell that doesn't have the standard sign is the standard E cell for that either the reduced or the oxidized, whichever one you have, plus 0.059 over Z. What was Z again? Moles of electrons transferred in the equation. And then log, wait to do my parentheses. Log, but it is multiplied directly to this. Log of your oxidized concentration over your reduced concentration. Like that. So the oxidized form over the reduced form, and it has to be in molarity. Yes, that's all.
What does this E stand for?
The moles of electrons transferred. So that was 3 and 4 and 5. This is actually the last one. I just ran out of space because I wrote the note at the bottom. The last one is the relationship between E cell and delta G. Does anybody remember what that is? Delta G equals negative N F E.
Maybe not. You're good.
And what this actually tells you is that the signs of delta G and E for a reaction to be spontaneous are opposite. So if delta G is spontaneous negative, then E cell is spontaneous when it's positive. So those two are always opposite to each other. So this actually tells us E cell spontaneous reaction.
Does it have to be standard?
It can be used with a non-standard E cell. You would just plug in regular E cell instead. So if it's non-standard, you just do E cell. Just whatever the E is. That's just how you compare the two. So if you had a combination with Nernst equation, then you would very well plug in a non-standard E cell in there. That's the last equation for this unit. N stands for here the number of electrons transferred. Don't ask me why they use 2 different letters to describe the same thing. F is Faraday, and then E cell is just E cell. So here, moles of electron transfer to Z. Here, moles of electron transfer to Z. N is the usual letter for moles.
What is the arrow thing for the whole point in Z?
What?
The arrow point is
Moles of electrons transferred. Same thing as that. They're the same thing. All right, so then that's just the straight up formulas for this unit. And this is a math heavy, formula heavy unit in terms of solving questions when it shows up. But there was a topic that you might have forgotten about in electrolysis because it shows up sometimes, not always. It's called electrolysis. What's electrolysis? Because there's actually 2 types of electrochemistry. One is electrolysis, One is using electrolytic or galvanic cells. So what's electrolysis? What's that process? Yes.
Breaking apart ionic compounds using electricity.
Almost exactly what I said. And so this is not a Cambridge definition to memorize, but it's good to know exactly when you use this. So I'm going to write out what it is. Electrolysis is using electricity and it's basically to split a compound into its elements in standard state. And although I had originally said ionic compound, I didn't write ionic compounds right now because it doesn't only apply to ionic compounds, it also very famously applies to water. You can electrolyze water. And so it's really just that concept of using electricity to split a compound back into its elements in standard state. This is a non-spontaneous process, which is why you have to use electricity in order to do it. You need a battery or some source of electricity, some source of energy in order to accomplish this. And I wanted to show you an example. An example would be electrolyzing or electrolysis of NaCl liquid. What do I mean by liquid? Molten. So for ionic compounds, they have to be molten to be electrolyzed. If they are aqueous, you will likely not electrolyze the compound. Instead, you may electrolyze water or part of it. So this is molten. This indicates that it has been heated to a really, really high temperature. So you have that movement of electrons going on. So then what would be oxidized here in the electrolysis of NaCl? Because this is the type of questions that they ask, where they ask you for the half equation for what is being oxidized and what is being reduced. The chlorine. So you would write it as it naturally first exists, which is Cl minus. And if it's being oxidized, it's turning into Cl2 1/2, right? Or put a 2 in front of there, but I put the 1/2 here. And then where would I put the electron, on the left or the right side? It's being oxidized, so the electron is being gained or lost. So on the wrong side. And so then what would be reduced? Sodium. And it would be going from Na plus to Na. So as a result, you're actually taking NaCl and you're turning it into chlorine gas and pure sodium. What if we were talking about aqueous solutions, though? Yes.
Sorry, I thought this was for the ions. It's liquid, right?
It would be liquid, yeah. Because that has to be molten. What if it's aqueous?
Yes.
So electrolysis in aqueous solution. Whenever you have an aqueous solution, this means you may very well, instead of electrolyzing your metal and your non-metal, you may be electrolyzing the hydrogen in water or the hydroxide in water. And so what you have to consider, if I am electrolyzing in aqueous solutions, and the way that I wrote it is like a little chart. It would be X plus versus H plus, and it would be Y minus of my ionic compound versus OH minus. The question is, in aqueous solutions, which one gets electrolyzed?
Yeah.
And this depends on something called, for your metals, the metal activity series. Now, I am not going to go ask you to memorize the whole metal activity series because I don't think you need to. If you have a group 1 or 2 metal, H plus is going to be the thing that gets electrolyzed because group 1 and 2 metals are too reactive. So if you have a group 1, 2 metal, H plus gets reduced. And what would that equation look like? If it's H plus that gets reduced, it would be H plus E minus goes to 1/2 H2. What metals are less reactive than H plus and would get reduced? So less reactive metals get reduced. And those metals are, I'm going to write it here. It's not all transition metals. Because actually there's a lot of them that are above H plus. The only ones that are below H plus that are of interest to you, that you care about, are copper, silver, and platinum, and gold. The precious metals, copper, silver, platinum, gold. So if you see any of those, they're going to get reduced. And the equation for that would be whatever the charge is plus E minus goes to X. So what about OH minus? How do we know if it's the ion that gets oxidized, oxidized, or if it's OH minus? So the idea is if it's polyatomic. If you have a polyatomic ion, then OH minus is easier to oxidize. The polyatomic ion is too large. So if polyatomic, if your Y is polyatomic, then OH minus gets oxidized. And you would need to know the equation for that. The equation for oxidizing OH minus is, and I'm going to help you create it right now, just a reminder, OH minus goes to the specific gas that gets released from OH minus is O2. But then we have to finish the rest. So what should I do first? I balance the oxygen. And then what about those hydrogens? Where do they come from? Like there's hydrogens on one side but not on the other. Do you remember what to do? What do? Add H plus. So I would add 2 H pluses to this side. Now what do I have to do? Balance. So how would I balance this? The electrons. Balance the electrons. The oxygens are balanced. The hydrogens are balanced. This has a +2 charge. This has a -2 charge. Which side gets electrons and how many? It's the product side, and it would be 4. 4 electrons. So this would be the correct equation for OH minus. Now, could you half this and make this 1 OH minus, 1/2 O2, 1 H plus, and 2 E minus? Absolutely, same equation. Yes. Less reactive metals get reduced. And then it says here, these are the actual less reactive metals that get reduced. So then, continuing on Y versus OH minus. When would Y get oxidized specifically? Because there are some anions that get oxidized and not OH minus. Which ones? Halogens. So if you have a halide, the halide gets oxidized. In general. And so this would go Y minus goes to Y2 actually, right? Because halides go to Y2. 1/2. And then plus E minus because all the halogens are diatomic. You, for paper 4, in the standards, and I have the standards in front of me for electrolysis, they tell us specifically to predict the identities of the substances liberated during electrolysis from the state of the electrolyte, molten or aqueous. State and apply the relationship F equals LE, calculate the quantity of charge, calculate the mass of volume, determine the Avogadro constant. So there are no standards about memorizing the anode and the cathode for electrolysis. You only have to do it for galvanic cells. That's good news because that means for like the charge of the anode and the cathode, they're switched for the two of them. You only have to memorize it for galvanic voltaic cells, not for this type of cell. This is all you have to know along with the math for electrolysis. So making that clear. You do not have to memorize, like you like to call the bucket. For electrolysis, you only have to memorize it for the spontaneous reactions, which are called electrolytic cells from Cambridge. So electrolysis versus electrolytic cell. Cambridge calls these electrolytic cells. I learned them as voltaic cells. Some people call them galvanic cells. In chemistry, one of the things that are confusing is there are so many synonyms that describe the same thing. Yes.
Could I ask, what did you like right below the 8 plus E minus?
Here,
Yeah.
less reactive metals get reduced. Just ran out of space. And then it says here, these are the ones that get reduced. So electrolytic cells, which are also known as galvanic cells. Yes, and we did learn about the Daniel cell, and somehow that's like just a very specific of the galvanic cells that exist. That's something if you're studying for National Science Bowl next year, is something you may want to add into your repertoire of things to memorize. But it's not on the Cambridge exam. If it was, they'll tell you what it is. Electrolytic cells / galvanic cells. These are what we use for generation of chemical energy. What do I mean by that? These cells produce electricity. They don't require electricity, they produce electricity. From the difference in cell potentials. Of what's being oxidized and what's being reduced. And what is reduced. This is where most of the standards are at and where you need to draw what you all like to call the buckets, but it's really the anode and the cathode.
I think it's just look at the all these buckets.
You cannot call them buckets on Cambridge, or at least I wouldn't do it if I were you. So this would be the.
Imagine you put like beakers and then you put parentheses buckets.
I want to call this electrochemical. You should change that to electrochemical. And let me double check the standard here. It says. It doesn't say in the standard, but I would call them electrochemical cells. Would be the best way to call them. Electrochemical. All right, so I would write out a general idea of how your cells should look, which is you should have this. You should have this. That. You should have a salt bridge. And what's at the top? And just as a side note, we put the electrodes above the water level because we needed the alligator clips to be above the water level. But in a more fancy setup, you would actually have them inside the water level. So I'm just going to leave them like this because that's how I've seen them on all the Cambridge exams. This right here is your voltmeter, which you're allowed to just put a V there, and it's understood by Cambridge. You understand that that's a voltmeter. You can choose either side to be your anode and your cathode. However, electron flow depends on what side you put as your anode and what side as you put as your cathode. Most people put anode on the left side and cathode on the right side. But technically, if you did it the other way, it just means you have to write your arrows for direction of electron flow, the opposite direction. Yes.
What about like a bottle for gas?
dispensing or whatever.
That's for a specific system. So we're going to talk about that momentarily. One of the first things you should know is that the cathode is positive here. Cathode is the positive electrode. And that's because it needs to have the ability to attract electrons to it. So in order for it to attract electrons to it, it has to be positive because the electrons are negative. And the anode is negatively charged. So the negative electrode is the anode and the positive electrode is the cathode. The next thing to note is that electron flow is from the anode to the cathode. Where would I write the direction of electron flow? So let's say that this is my anode, which is typical, and this is my cathode. I write it that way. How would I write my direction of electron flow? If this is my anode and this is my cathode, where would the electrons be going through? Would they be going through the wire or would they be going through the salt bridge?
Anode.
It would be from anode to cathode, and you write it like this. BE minus. The electron flow is like from left to right, and you're allowed to say left to right, but that's as long as you've written your anode on the left and your cathode on the right, because sometimes they ask you, it's one of the standards, direction of electron flow. If you say left to right, then you better have written your anode on the left and your cathode on the right. If you flipped them, then you write it the opposite direction. Got it? And so electrons go through the wire. What goes through the salt bridge to maintain the charge balance? It's actually ions flow through the salt bridge, through the little gel that's there or whatever paper you have. The ions that you have in the solution keeping the charge balance, the ions flow through the salt bridge, and you have to have the salt bridge or you don't complete the circuit. But it allows for not one side to build too much electrons. It allows for there to be a charge balance throughout the whole system. And so you need the salt bridge or you're not going to have a circuit for these electrochemical cells. All right, so then the salt bridge, I said this, but I want to make sure you know it because they could ask. The salt bridge is to complete the circuit. And maintain charge balance. So what about types of cells? What about the identity of electrodes? Identity of electrodes. No, what is the identity of the anode and what is the identity of the cathode? So what is the identity of the electrodes? How would we know? How do we know when it's the metal versus when it's platinum?
Like if they're ions or whatever, it's gonna be platinum.
Yeah. So if you have a metal ion system, it's the metal. If it's two transition metals that are differently charged, so we call that metal ion, then the electrode is made out of platinum. Not any metal, not the metal that's made of that system, but of platinum. And what if it's a non-metal system? It's also platinum. Non-metal is platinum, which means the She is platinum, which we'll do on the next slide because I ran out of space. I'm going to pause and go to the next slide shortly. We have a couple things to go over. We have to go over the sheet and we have to go over the definition still. Ready?
No.
No?
Thank you.
I'll pass.
Go back.
What? Oh, to go back. Good now?
Miss, which metal is it? If it's both metal and metal ion.
The metal.
Oh.
So copper, copper 2 plus would be copper. Fe 2 plus would be Fe. Cobalt, cobalt 2 plus would be cobalt. Zinc 2 plus would be zinc. Yes? It's whatever the metal is. Can't specify. Sure, what? Huh? Doubt. Continue? Okay, so on the back, we now need to talk about the sheet. What is the sheet? Which, by the way, is a platinum electrode. Is the electrode you use for the sheet. What is the sheet? Standard hydrogen electrode. And so you have to not only know what the sheet is, but you have to know how to draw it. And so the purpose of the sheet is to set a standard potential. It's your reference cell. So it's your reference electrode, where the standard is set at 0.00 volts. So everything else, any metal or non-metal you combine with the sheet, is either going to be oxidized in comparison to the sheet or reduced in comparison to the sheet. The sheet is set at 0, and you can compare the numbers above or below 0. And we'll talk about the numbers again in a moment. But that's what the purpose of the sheet is.
Hey, she is still like electrochemical.
Yes, it is part of the electrochemical cells. Galvanic cells, voltaic cells, however they call it. But Cambridge will call it electrochemical. All right, so reference electrode where the standard is set at 0 volts. This allows us to measure. So it allows for measurement of potential values for any other ion compared to it. So it allows for measurement of other substances ESA values. So they're either going to be positive or negative compared to the sheet. What would happen if they're positive compared to the sheet? So positive compared to sheet means more easily reduced. And if it's negative compared to the sheet, it means more easily oxidized. So positive E cell values compared to the sheet are reduced, and negative are oxidized. And it's really that same pattern. The more positive your E cell value, the more likely what you have is going to be reduced, and the more negative your E cell value, the more likely whatever that substance is going to be oxidized. And so what is the design of the sheet? So the half cell of the sheet. What does it look like? One bucket for one half. And then what? In here goes your, what's the electrode? The T. How do I write the gas? Do you remember how to write the gas if there's a gas coming out of a half cell? Write like a little, like that, right? Remember that? Because you've got gas in the sheet. And what was the concentration of acid, if you remember?
What, trust?
The concentration is always 1. All BMI squared. Because it's standard. And then you would, have your electrons going out. And then this would be H2. Because it's the standard hydrogen electrode, so it's H2 gas. That's the half cell drawing for the sheet. What are the standard conditions? Besides the 1 molarity that you also have to know?
1 atmosphere.
1 atmosphere. And what temperature? 298 Kelvin. Yeah, we don't run it at freezing. If we said 0 degrees Celsius, we said we'd be running the reaction at freezing temperature. We run it at lab conditions.
Oh.
All right, the last 2 things. We're actually, like I said, we finished. Yes. I'm so glad that this was the unit for today. When we had the meeting versus some of the other units that are much more hefty.
Like ultimate gambles.
Ultimate gamble. I had no idea. It just worked. Or y'all got lucky. Definitions.
Not skilled.
Not skill. By design. We'll just say by design. Okay, so there are literally only 2 definitions in the Cambridge standards for this unit. So one of the things about paper 4 is that you can guarantee every unit's going to be there. And so when this unit shows up, it is likely they will pick one of these 2 definitions for you to just write the straight up answer to. The first one is standard electrode potential.
50-50.
You have a 50-50 chance. And they're actually very similar definitions to each other, just be careful to look at the key difference. So the standard electrode potential is the voltage produced when a standard half cell of whatever you have, standard half cell is connected to the sheet, and you are allowed to write SHE. You do not have to say fully the standard hydrogen electrode. That is an allowable abbreviation. So voltage produced when a standard half cell is connected to the sheet under standard conditions. And could they ask you for those standard conditions? They could, right? Some questions say yes, some questions say no. And so the standard conditions I'm going to put here that you have to know again are 1 molarity of whatever your solutions are. They have to be 1 molarity. Otherwise, we're using Nernst equation to change the amounts. So 1 molarity solutions of whatever you have. And then it's 1 atmosphere and 4×10⁵ pascals and 298 K. That's the 1 definition, standard electrode potential. The second definition is standard cell potential. And the only difference between these 2 definitions, in standard electrode potential, you're comparing to the sheet. In standard cell potential, you're comparing 2 half cells to each other. So it's not against the sheet. It's like magnesium versus zinc. It's zinc versus copper. It's copper versus silver. It's like whatever the 2 metals or non-metals or whatever it is you're comparing to each other. So the definition for standard cell potential is just the difference in standard electrode potential between 2 half cells. It's the formula, E red minus E ox. But in words, the difference in standard electrode potential between 2 half cells. That's it. Those are the only 2 definitions here. So I've got all the standards. I've been picking them out of the syllabus so you can see exactly what it is you need to work on for this unit of study. Expect unit 4 to be a lot more hefty, especially since there were 2 parts, kinetics and transition metals. But this was electrochemistry. There you go. There you go. Remember, if you get a design question where you have to design your electrochemical cell, those are typically worth 3 or 4 marks. And if you get a calculation with the quick formula, that's also usually about 3 marks. Like it was in the Bower. All right, we've got a phone call. Let's see who we got. Hello, this is Miss Williams. Who? Daniela Gutierrez? Okay, no problem. Daniela Gutierrez, go downstairs. Yes. Yes, you can sketch your own go at this time. Give me a few minutes then. All right, we're in the last 10 minutes of class, so just finish writing down whatever it was, and you can either start working on the homework that I posted. Yep, there's homework. Or you can take a break because you are in that last 10 minutes of class. How would you like to 30?
I don't know.
Give me your.
Yeah, this one's good.
You have it, right?
You didn't study.
No.
The end bag.
You have it, right?
Fortunately, not a thing.
You're right. Very small.
Fortunately, not a thing.
Okay.
Sam trying to invent more testing.
Wait, are you like
That
for
one
the?
said,
Okay, did you study Faraday for the English?
you don't have enough tests?
Daniel, did you study Faraday? Did you study Faraday for the English?
Yep, I'm taking the English quarterly because I missed the He does got study Faraday's for.
For the English quarterly?
Apparently that's gonna be relevant.
Yeah, Faraday sounds like an
It
English.
is the Faraday
Does not
for
sound like an
English.
English theory. Does this name not sound like an English theory? You can't tell me he doesn't. I mean, he's basically English, okay? He's basically an English theory.
Who?
Sounds like an English.
That's not how that works.
What?
Because Faraday is basically an English theory.
His name sounds like one, okay?
Faraday sounds like.
How do you feel about this unit?
I think it's easy and I think it's very interesting. I like the idea of
And it's energy generation. That's why I said, like, this one's a good one.
You know?
Or energy use, whichever way you do the reaction. Energy use or energy generation. You're welcome.
Actually, like stole from Faraday.
Actually, this is wild.
All English theories are still from Faraday?
Theorists in our